Welcome to CSS Breakdown, book by book, Season 07, Episode 04, where we crack open Atkinson and Hilgard's Introduction to Psychology 15th edition to unravel the astonishing mechanisms through which our minds perceive the world, starting with the very foundation of experience. Sensation.
Okay, so imagine this for a second. You're sitting in a deserted church, maybe late at night. Seems totally quiet, right? Serene.
Yeah, you'd think so.
But here's the thing. Our sources really drive home. Even there, you're just constantly being bombarded. It's this vast informational tapestry, they call it.
That's a great phrase.
Isn't it? Think about it. Even in silence, there's still light, faint sounds, the pressure of, the pew you're sitting on, maybe the smell of old wood or something. It's all there.
But what's really wild is how much doesn't register. All those microwave signals, radio waves, maybe a dog whistle outside.
Totally oblivious. They just wash right over us. We don't sense them.
Exactly. And that immediately brings up a couple of really big questions for psychology.
Okay, well, first, out of all that information floating around, why do only certain things actually get picked up by our senses? Like, why green light but not X-rays? They're both electromagnetic energy, right?
Yeah.
And the evolutionary angle, which Pinker talks about in How the Mind Works, is pretty compelling.
Yeah.
Basically, we evolved to perceive what helps us survive, what's useful.
So, like, green light helps us find plants or spot things, but X-rays just pass through stuff. Not very helpful for finding lunch.
Precisely.
Right.
Or radio waves, they just be a blur, useless for navigating. So, yeah, it's like an evolutionary filter.
Okay, that makes sense. So what's the second question?
The second one is, how do our sense organs actually grab that useful information efficiently? How do they take what they can get and turn it into something the brain can actually work with?
Right. And that's kind of what we're digging into today. So maybe we should start with this key distinction the book makes. Sensation versus perception.
Yes, absolutely crucial. Sensation is like the raw data, the fundamental experience. Your eye just registers, say, a big red shape.
It's the input stage. Involves the sense organs, the first nerve pathways.
Exactly. And perception is the next step. That's when your brain takes that raw red-shaped data, pulls it together, interprets it, and goes, aha, fire engine.
So it's about meaning, integration.
Right. Sensation is seeing red, perception is fire engine. And this deep dive, we're focusing mostly on sensation, how we get that initial info. Perception, the meaning-making part, that's really for the next chapter, chapter 5.
Gotcha. Though it's interesting they mention it's not a totally clean break between the two.
Oh, definitely not. It's more fluid. People like Damasio and Zicki have shown there are these back projections from higher brain areas.
Wait, so the brain sends signals back down?
Yeah, modifying how that initial sensory info is processed, even really early on. It's not just a one-way street, input then process. The brain's actively shaping what we sense from the get-go.
Wow, okay.
Is that good?
Yeah, that's pretty cool. So how are we going to tackle all this? What's the roadmap?
Well, we'll start with properties common to all senses. Then we'll zoom in on the big ones, vision and hearing, our main distance senses.
And then the other senses.
Right, the unsung heroes.
Mm-hmm.
Smell, taste, pressure, temperature, pain. Of course, in real life they all work together, but it helps to look at them one by one to understand the basics.
Sounds like a plan. Let's dive in.
Mm.
Yeah.
Okay, so the fundamental job, the core task for every single sense.
Yeah.
You called it transduction.
That's the one. Got to
Yep.
take information from the outside world, light, sound waves, chemicals, whatever, and convert it. Transduce it into neural signals, the language the brain understands.
Like changing currency, turning environmental energy into brain energy.
Exactly. And the two big things we look at for any stimulus are its intensity, how strong it is, and then, well, everything else. Its quality, its nature.
Intensity seems straightforward, maybe.
Yeah.
Stronger stimulus, stronger sensation.
Well, yes, but quantifying that relationship precisely, that's been the real challenge. How much stronger? And that leads us to thresholds. Ah, right. The absolute threshold. That's the minimum, yeah. The quietest sound, the dimmest light you can possibly detect.
Detect reliably, that is. Usually defined as 50% of the time in experiments.
Yeah.
And the examples are just staggering.
Like the candle flame, seeing it from 30 miles away on a clear, dark night.
Yeah. Or hearing a clock tick 20 feet away in total silence, tasting 1 teaspoon of sugar in 2 gallons of water.
Or smelling 1 drop of perfume diffuse through 6 rooms.
And touch. A fly's wing falling on your cheek from a centimeter. It's incredible sensitivity.
And this isn't just guesswork, right? They measure this stuff carefully. Psychophysical procedures.
Right. random stimulus presentations, finding that 50% detection point. It's statistical, but it tells us something fundamental.
It's like that Hecht, Schler, and Piren's study from 42, the one about vision being as sensitive as physically possible.
Wow, that's a classic. Humans detecting just 100 photons, but only, 7 actually hitting the key molecules.
And each hitting a different receptor, meaning each receptor can respond to a single photon.
It really is the physical limit. Our eyes are incredible detectors.
Okay, so that's the absolute minimum. What about telling things apart? Like, is this light brighter than that one?
That's the difference threshold, or the just noticeable difference, the JND. The smallest change in a stimulus you can reliably detect.
How do they measure that? Similar process.
Yeah, present a standard stimulus, then comparisons. Is this one brighter, dimmer? Until you pinpoint that minimal detectable difference.
And this leads to that really important law, Weber's law.
Fechner.
The Weber-Fechner law.
Oh.
Crucially, it says the JND isn't a fixed amount. It's proportional to the intensity of the original stimulus.
Okay, break that down. The candle example.
Right. If you had 25 candles lit, maybe you can just barely notice when 2 more are added. That's an 8% increase.
Okay.
So you started with 100 candles, you wouldn't notice just 2 more. You'd need 8% of 100, which is 8 more candles. See the difference. That percentage, that Weber fraction, stays constant. So our sensitivity to change depends on the starting point. Makes sense. Quiet room, whisper is loud. Rock concert, you gotta shout.
Exactly. And this has real-world uses. Theater lighting, they know they need a percentage increase for a subtle change. Soft drink companies calculating how much sweeter a drink needs to be to taste noticeably sweeter.
Even Twinkies, using preservatives below the absolute taste threshold so we don't notice them.
Precisely.
Clever, huh?
Okay, so that covers thresholds, detecting something versus nothing, and detecting differences. But most of the time, things are way above threshold. How do we perceive the intensity then?
That's where S.S. Stevens comes in. With his work on suprathreshold sensation, he developed Stevens' power law.
Power law sounds mathematical.
It is, a bit. Basically, the perceived psychological magnitude, how bright a light seems, how loud a sound feels, is a power function of its actual physical magnitude. The formula is simple. C equals F to the power of R.
C is perceived, F is physical.
Oh, what's that?
R is the magic number, the exponent. And it's different for different senses. That's the key insight.
Tell us.
Well, if R is less than 1, like for loudness or brightness, the curve bends downwards, meaning as the physical intensity goes up, the perceived sensation increases by smaller and smaller amounts. It compresses the range.
Okay, so double the sound energy doesn't sound twice as loud.
Right. It prevents our senses from being overwhelmed by really intense stimuli.
Yeah.
But if R is greater than 1, like for electric shock.
Oh, I bet that curve goes up sharply.
Exactly. Concave up. A small increase in physical intensity leads to a much larger increase in perceived pain.
That feels adaptive, like for safe things, compress the signal. For dangerous things, amplify it. Make sure you notice.
That's exactly the thinking. It's a survival mechanism. Light and sound are usually benign, so we handle a huge range. Pain, potential damage, the system screams at you, get away, now.
Wow. Okay. That makes a lot of sense. Now, speaking of survival and dealing with information, signal detection theory. This sounds important.
It's huge, because information in the real world is never pure. There's always the signal, the thing you're trying to detect, mixed in with noise, irrelevant background stuff.
Like trying to hear your phone ring at a noisy party. The ring is the signal, the party is the noise.
Perfect example. And in any detection task, you can have a hit correctly detecting the signal, or a false alarm thinking you detected it when it wasn't there.
Or misses and correct rejections, too.
Right. But the crucial insight of signal detection theory is that it lets us separate two things. The observer's actual sensitivity, how good they really are at telling signal from noise, and their bias, how willing they are to say, yes, I detected it.
Bias, like being cautious versus being trigger happy.
Exactly. Think of 2 airport screeners. Charlotte is very cautious, only calls out a bag if she's absolutely sure. Linda is more liberal, calls out anything even slightly suspicious. They might have the same sensitivity, the same ability to spot weapons, but their bias leads to different numbers of hits and false alarms.
Okay, I see. And the book uses that radiologist lawsuit example.
Yeah. The case of Dr. A missing a small tumor, and Dr. B, the expert witness, easily spotting it later after seeing x-rays where it was much larger.
So Dr. B claimed Dr. A wasn't sensitive enough, right? Negligent.
But signal detection theory offers another explanation. Dr. B, knowing there was a tumor and having just seen the later x-rays, likely had a huge bias towards saying, yes, I see it on the original film. His expectation was sky high.
Whereas Dr. A had no reason to expect a tumor there specifically.
Right. So was Dr. B actually more sensitive or just more biased? We can't know without applying signal detection analysis. It's vital in medicine, security, anywhere. Detecting faint signals matters. You have to separate ability from willingness to guess.
That's really powerful. Okay, so we detect signals based on the sensitivity and bias, but how does the sensory information actually get coded in the brain? It's not like little pictures or sounds travel up the nerves, right?
Definitely not.
Oh.
Forget those old sci-fi movies like Fantastic Voyage where tiny people see red blogs near the eye. Our experience, the redness of red, the sharpness of pain, it's all about patterns of neural activity in the brain.
So the stimulus itself doesn't reach the brain, just signals about it.
Precisely. The conversion, that transaction we talked about, happens at the receptors. Specialized cells in your eyes, ears, skin, nose, tongue. They translate physical energy, light, vibration, pressure, chemicals into electrical nerve impulses.
And the brain interprets those impulses, like Wilder-Penfield's experiments, stimulating the brain directly.
Incredible work. He'd stimulate parts of the parietal lobe and awake patients during surgery, and they'd report feeling tingling in specific body parts, a finger, a lip. Proving sensation happens in the brain, triggered by neural activity, not just in the skin.
So how does the brain code intensity using those nerve impulses? A stronger touch feels different from a light one.
Primarily through the rate of firing. More intense stimulus, faster firing rate from the neurons involved.
Yeah.
Simple pressure might cause slow, irregular firing. A hard push causes rapid, sustained firing.
Are there other ways?
Yeah, the temporal pattern of the impulses can carry information, and also just the sheer number of neurons activated. More intense stimulus usually recruits more neurons.
Okay, rate, pattern, number of neurons for intensity. What about quality? How do we tell sight from sound, or red from green, or sweet from sour?
Well, distinguishing between senses sight, sound, touch relies on Johannes Müller's idea of specific nerve energies. Basically, different senses use different nerves that go to different dedicated areas in the cortex. The visual cortex gets signals from the eyes, auditory cortex from the ears, and so on. The brain knows its sight because the signal arrived in the visual area.
Makes sense. But within a sense, like red versus green, or sweet versus sour.
That's more complex. It seems to involve both specificity and patterning.
Specificity, like a red neuron and a green neuron.
Sort of. Some neurons or nerve fibers respond best to certain qualities. We might have sweet fibers in taste, for example, but it's rarely that simple.
So patterning.
Yeah. More likely, the stimulus say, the taste of strawberry activates a whole pattern of firing across many different fibers. Some fire fast, some slow, some not at all. That unique overall pattern is the brain's code for strawberry.
So it's a combination. Specific neurons tuned to certain things, but the overall experience comes from the combined pattern across many neurons.
That seems to be the current understanding for coding quality within a sense. Both mechanisms are likely at play.
All right, let's zoom in on vision, our primary sense for navigating the world at a distance, right?
Absolutely. And the stimulus, the raw material, is light, electromagnetic energy.
But as you said, we only see a tiny slice of it, the visible spectrum.
Just that little band between roughly 400 and 700 nanometers. Everything else, gamma rays, X-rays, UV, infrared, microwaves, radio waves, totally invisible to our eyes.
It's amazing how much is out there that we just don't perceive. So how does the eye capture that visible slice?
Think of it like a biological camera. Light first passes through the cornea, the clear front surface, then through the pupil, that black hole in the middle.
Which gets bigger or smaller depending on the light. Controlled by the iris, the colored part?
Exactly. The iris adjusts the pupil size. Then the light hits the lens, which focuses the light onto the retina at the very back of the eyeball.
And the lens changes shape to focus, right? That's why some people need glasses nearsighted, farsighted.
Precisely. Or why reading glasses become common as we age, the lens gets less flexible.
So the light image lands on the retina. What happens there? That's where the receptors are.
Yes. The retina is the transduction hub, packed with two types of photoreceptor cells, rods and cones.
Rods and cones. Okay, what's the difference?
Big differences. Rods are your night vision specialists. They work in very dim light, but they don't see color, and the image they provide is kind of grainy low resolution. They're mostly found in the periphery of your retina.
Okay, so rods equaled dim light, black and white, periphery. What about cones?
Cones are for daylight vision. They need much more light to function, but they give you sharp, detailed, high-resolution color vision. And they're heavily concentrated right in the center of your retina in a small pit called the fovea.
So that's why we look directly at things we want to see clearly, to get the image on the fovea where the cones are densest.
Exactly. Inside both rods and cones are photopigments that absorb light, kicking off the neural signal. Those signals then pass through other layers of cells in the retina.
And eventually bundle together to form the optic nerve, which carries the info to the brain.
Right. And interestingly, where that optic nerve bundle leaves the eye, there's no room for receptors. That creates a blind spot.
But we don't notice a hole in our vision.
Nope. Your brain cleverly fills in the gap based on the surrounding information. Seamlessly.
Amazing. Okay, so thinking about light sensitivity, those differences between rods and cones are key.
Absolutely. Cones rule the day, rods rule the night. Their wiring is also different. Cones often have nearly a one-to-one connection with the next layer of cells, which gives you that high acuity, great for reading fine print.
But rods?
Many rods often converge onto a single downstream cell. This sums up faint signals, making rods much more sensitive to dim light. But you lose the fine detail. It's a trade-off. Sensitivity versus resolution.
Which explains why looking slightly beside a dim star helps you see it better. You're using your peripheral rods.
Precisely. You're putting the star's faint light onto the most sensitive part of your retina for night vision.
And this leads to dark adaptation, right? Walking into a dark room from sunlight.
Yes. That process where your eyes gradually become much more sensitive to light, two things happen. Your pupils dilate, letting in more light.
But that's pretty fast. The slow part is the chemistry.
Right. The main adjustment is the slow regeneration of those light-sensitive photopigments in the rods and cones, especially the rods. They become much more effective at capturing photons.
And the dark adaptation curve shows this. A faster cone adaptation phase than a slower, deeper rod phase.
Exactly. Which explains that pilot trick wearing red goggles before night flight. Red light mainly stimulates cones, so it lets the rods dark adapt undisturbed.
Clever.
Very clever. Okay, moving from sensitivity to seeing patterns. Visual acuity, like the eye chart.
Right, the ability to resolve fine details. And the most basic element of any visual pattern, the book says, is an edge or a contour, where light meets dark.
And our visual system is actually built to enhance those edges. It is. Through a process called lateral inhibition. The Hermann grid illusion is a great way to see it.
The grid with the gray smudges at the intersections.
That's the one. You see those ghostly smudges in your peripheral vision, but not at the intersection you're looking at directly.
Why does that happen?
It's the wiring. Retinal cells, when stimulated by light, tend to inhibit their neighbors. At the intersections, a cell receives more inhibition from the surrounding bright areas, making it fire less, so it looks dimmer, hence the gray smudge.
But why not where you're looking directly at the fovea?
Because the range of that inhibition is much smaller at the fovea, contributing to its higher acuity. The effect is stronger in the periphery, where the inhibitory fields are larger. It's a built-in edge detector.
Neural processing literally creating what we see. Wow. Okay, let's talk color.
Right. Different wavelengths, different colors. Short waves look blue, medium green, long red, roughly speaking.
And color has dimensions, like hue, brightness.
Exactly. Hue is the color name, red, blue, green. Brightness is the intensity, how much light is reflected. And saturation is the purity, think vivid red versus pale pink or grayish red. The Munsell system organizes these into a kind of 3D color solid.
And we're pretty good at telling colors apart.
Amazingly good. About 150 distinct hues, but factor in brightness and saturation, and we can discriminate over 7 million different colors. The J&D for wavelength is tiny, just a couple of nanometers in some parts of the spectrum.
So how do we actually see all these colors? The key seems to be color mixture.
Yes. You only need 3 primary lights, typically red, green, and blue, mixed in different proportions to create almost any color we can perceive.
Which leads to metamers, different physical mixtures of light that look identical to us.
Exactly. A pure yellow light might look identical to a specific mixture of red and green light. Our eyes can't tell the physical difference.
Seems like we're losing information there.
But it's adaptive. Our visual system simplifies the input. If we had to process every single wavelength uniquely, it would be overwhelming. Relying on just 3 channels is efficient. It's why TV and computer screens work tiny red, green, and blue dots, creating all the colors.
Makes sense. And this links to color deficiencies.
Right. People who are dichromats only need 2 primaries to match colors, and they confuse certain hues, like red and green most commonly. Monochromats are truly colorblind, seeing only shades of gray. These are usually genetic, much more common in males.
Now, the theories of color vision, this was a big historical debate, wasn't it? Trichromatic versus opponent process.
It was. But the cool thing is, they both turned out to be right, just operating at different stages. First, the trichromatic theory from Young and Helmholtz. Even before cones were discovered, they proposed 3 receptor types, each most sensitive to different wavelengths, short, beating green, long red.
And color perception depends on the ratio of activity between these three.
Exactly. This explains color matching really well, and most color deficiencies like lacking one type of cone.
But then Herring came along with the opponent color theory, based on observations like,
Right.
you can't see reddish-green.
Right, or yeller's blue. And those weird after images stare at red, look away, see green.
Yeah.
Herring proposed opponent pairs, a red-green unit and a blue-yellow unit. Activity in one direction signals one color, activity in the other signals its opponent.
So how did they reconcile these?
The two-stage integration. It turns out the trichromatic part happens first, at the level of the cones. There really are three types of cones sensitive to short, medium, and long wavelengths.
Okay.
But then, signals from these cones feed into opponent process cells at a higher level, like in the thalamus. So you might have a cell excited by red cone signals, but inhibited by green cone signals. That's your red-green opponent unit.
Ah, so the theories weren't rivals, they described different stages of processing.
Exactly. Finding those actual opponent neurons biologically was a huge confirmation. A beautiful example of psychology and biology converging.
That really is elegant. And tying this back to the sensation perception bridge, they use that Scarlett Johansson example.
Yeah, seeing someone approach from a distance. As they get closer, the image on your retina gets bigger, sharper, less blurred. You perceive more detail.
And researchers can actually quantify that blurring, show what seeing someone from, say, 50 feet away looks like.
They can, which has practical uses, like in court. How well could a witness really see the defendant from that distance? Showing the jury an equivalently blurred image makes it much more concrete.
Connects the lab science right back to real life.
Very cool.
Yeah.
Okay, let's switch gears to audition. Hearing. Another crucial distance sense.
Definitely. Communication, music, warnings.
It's fundamental.
That's
And it all starts with tiny pressure changes in the air.
sound waves, right? Caused by vibrations.
Exactly. Something vibrates vocal cords, a guitar string, leaves rustling, creating pressure waves that travel through the air.
Yeah.
We could describe simple pure tones using sine waves.
And those waves have two key properties, frequency and amplitude.
Right, frequency is how many cycles per second measured in hertz. That corresponds to our perception of pitch. Higher frequency, higher pitch.
And amplitude.
That's the intensity, the amount of pressure change in the wave. It corresponds to our perception of loudness. We measure it in decibels, dB.
Which is a logarithmic scale, isn't it? So a small dB increase means a big pressure increase?
Yes, 10 dB is a 10-fold increase in sound energy. And it's important sustained exposure to sounds over, say, 100 dB, like loud concerts or machinery, can cause permanent hearing damage.
Good reminder. What about the quality of sound, besides pitch and loudness, like telling a violin from a trumpet playing the same note?
That's timbre. It relates to the complexity of the sound wave, the mixture of the fundamental frequency, and its overtones. It's the sound's unique fingerprint.
Okay, so how does the ear capture these waves? It's got parts, right? Outer, middle, inner.
It does. The outer ear, the curvy part you see, the pinna, and the auditory canal basically funnels sound waves towards the eardrum.
Which then vibrates.
Yes, and those vibrations are passed through the middle ear, which is an air-filled space containing three tiny bones, the smallest bones of your body, actually. The malleus, indices, and stapes. Hammer, anvil, stirrup.
And they transmit the vibration.
They do, acting like levers, amplifying the pressure significantly as they transmit it to the oval window, which is the entry point to the inner ear.
So the middle ear boosts the signal.
Considerably, by about 20 times. It's crucial for transferring energy from air vibrations to the fluid-filled inner ear.
Okay, so the inner ear, that's where the cochlea is, the snail shell.
That's right. The cochlea is a coiled, fluid-filled tube. Running down its center is the basilar membrane. And resting on that membrane are the crucial hair cells, the actual auditory receptors.
So pressure at the oval window makes the fluid move, makes the membrane wiggle.
Which bends the tiny hairs on top of the hair cells. That bending is the mechanical trigger that generates an electrical signal. That's transduction in the ear. Those signals then form the auditory nerve.
Incredible mechanics. Now, hearing intensity or loudness, are we equally sensitive to all frequencies?
No. Just like vision isn't equally sensitive to all wavelengths, we're generally most sensitive to intermediate frequencies, which conveniently includes much of the range of human speech.
And hearing loss. There are different types.
Broadly, yes. Conduction loss involves problems in the outer or middle ear, maybe a damaged eardrum or issues with those little bones. This tends to affect all frequencies fairly equally.
Okay. And the other type?
Sensory neural loss. This is damage to the inner ear, usually the hair cells, or the auditory nerve itself. This often affects higher frequencies much more severely.
And that's the kind associated with aging and noise exposure, like Pete Townsend.
Yes, unfortunately, those delicate hair cells, once damaged, don't typically regenerate. Protect your ears.
Definitely. How about locating sounds? How do we know where something is coming from?
Our brain uses clever tricks based on having two ears. If a sound is off to your right, it hits your right ear slightly sooner and slightly louder than your left ear.
Because your head casts a sound shadow.
Exactly. And the brain analyzes these tiny time and intensity differences between the ears to calculate the sound's location. Pretty sophisticated processing.
It really is. Okay, pitch perception. Higher frequency equals higher pitch. Can we tell small differences?
We're very good at it. The J&D for pitch is remarkably small, especially in the ranges important for music and speech.
And mixing sounds. You said it's different from light. If you mix pure tones, you can often still hear the individual notes.
Often, yes. Which suggests the auditory system might analyze frequencies somewhat differently than the visual system analyzes wavelengths. This leads us to the theories of pitch perception.
Right. Place versus temporal.
Exactly. The temporal theory, sometimes called frequency theory, originally suggested the whole basilar membrane vibrates at the same frequency as the incoming sound wave. This vibration rate dictates the nerve firing rate, which the brain reads as pitch.
But you mentioned a problem. Neurons can't fire fast enough for high pitches.
Right. Individual neurons max out around 1,000 hertz, but we hear pitches way higher than that. The Volley principle, groups of neurons firing in rotation, helps extend the range up to maybe 4,000, 5,000 hertz, but it still doesn't fully explain our perception of the highest pitches.
So that brings in place theory.
Yes. Championed by Helmholtz, building on earlier ideas, and really nailed down by Georg von Békesy's Nobel-winning work. Place theory proposes that different frequencies cause maximum vibration at different places along the basilar membrane.
How does that work?
The membrane is narrower and stiffer near the oval window, the base, and wider and floppier at the other end, the apex. High frequencies cause the biggest wave near the base. Low frequencies create a wave that travels further down towards the apex. The brain determines pitch based on which place along the membrane is most active.
So which theory is right?
Turns out, we need both. It's another elegant integration. Temporal theory, using firing rate and volleying, seems to work best for low frequencies, up to around 4,000, 5,000 hertz. Place theory works best for high frequencies.
And the middle range.
That's where it's a bit fuzzier. Both mechanisms might contribute in that intermediate range. But again, it shows how science often combines initially competing ideas to get a fuller picture.
Okay, let's move on to those other senses, starting with olfaction, smell.
A very old, very primitive sense, and incredibly important for survival, detecting spoiled food, smoke, gas leaks.
And it has a really direct route to the brain, right? Unlike other senses.
Yeah, the olfactory receptors high up in your nasal cavity send signals directly to the olfactory bulb in the brain, without going through the thalamus first, like most other sensory info. And the receptors themselves are basically exposed neurons.
Wow. Animals are way better at this than us, generally. Dogs, obviously.
Incredibly sensitive, detecting tiny concentrations we wouldn't even notice. Useful for finding drugs, bombs, missing people. And many animals rely heavily on pheromones, chemical signals for communication. Think moths attracting mates, or ants marking trails or signaling danger.
Do humans use pheromones like that?
Not in the same dramatic, automatic way as insects, but there's evidence we are sensitive to certain body odors. We can often identify our own scent, distinguish male from female scents.
And that thing about menstrual cycles syncing up in women living together, is that pheromonal?
It's suggested that subtle olfactory cues might play a role, yes. But it seems to be more of a physiological influence rather than triggering specific behaviors like in many animals.
Okay. So how does the olfactory system actually work? What's the stimulus?
Volatile molecules, things that evaporate easily and can dissolve in fat carried in the air. They reach receptors high in the nasal cavity, bind to them, trigger transduction.
And the signals go straight to the olfactory bulb, then the olfactory cortex, areas linked to memory and emotion.
Exactly, which might be why smells can trigger such powerful, vivid memories, that Proustian effect you mentioned.
How many smells can we distinguish?
Estimates vary, but somewhere between 10,000 and maybe even 40,000 different odors. Women generally tend to be better at identifying smells than men. We have around 1,000 different types of olfactory receptors, and the code for a specific smell seems to be the unique pattern of activation across these many receptor types.
Okay, on to gustation, taste, which is often confused with flavor, right?
Totally. Flavor is really a combination of taste and smell, plus texture, temperature. When you have a bad cold and food tastes bland, it's mostly because your sense of smell is blocked.
But taste itself is distinct. What influences it?
Genetics plays a role, like how sensitive you are to the bitterness of caffeine or the artificial sweetener saccharin, and experience matters too. Cultural diets shape preferences.
How does taste work mechanically?
The stimuli are substances dissolved in saliva. Receptors are clustered in taste buds, mostly on the tongue, but also on the roof of the mouth and in the throat.
And those tongue maps, sweet at the tip, sour at the sides, are they accurate?
They're a huge oversimplification. While there might be slight regional differences in sensitivity, you can taste all the basic qualities pretty much anywhere on the tongue where there are taste buds. The maps ignore complex nerve interactions.
What are the basic tastes?
There is strong agreement on 4: sweet, sour, salty, and bitter. Some argue for a 5th, umami, savory, and maybe others like fat taste. Coding seems to involve both specific fibers tuned best to one taste and also the overall pattern of activity across many fibers. And again, like smell, taste is surprisingly influenced by our minds. The cognitive influence.
Like the wine study. Tasted better if labeled expensive.
Exactly. Plasman's study showed identical wine not only rated as more pleasurable when participants thought it was pricier, but it actually triggered more activity in brain areas associated with pleasure.
So expectation literally changed the brain's response and the sensory experience.
Yeah, and Rachel Hurst found something similar with perfume labeled natural versus synthetic. Our beliefs shape our senses.
Amazing. Okay, quickly, the skin senses, pressure, temperature, pain.
Right. Pressure sensitivity varies hugely across the body. Lips and fingertips very sensitive, back less so. And it adapts quickly. You stop noticing the feeling of your clothes unless you focus on it.
Temperature uses separate receptors for warming and cooling.
Yes, cold receptors respond to temperature drops and extreme heat. Warm receptors to increases. We're very sensitive to small changes. And again, adaptation is strong. Think of the jumping into a cold pool. Feels freezing at first, then less so.
Which brings us to pain, the essential alarm system.
Absolutely crucial. That rare condition where people can't feel pain, it's devastating. They suffer constant injuries, infections. Without realizing it, pain keeps us safe.
What triggers it?
Any stimulus intense enough to potentially cause tissue damage, extreme pressure, heat, cold, certain chemicals. The receptors are mostly free nerve endings.
And there are different kinds of pain, sharp versus dull.
Yes, phasic pain is the sharp, immediate ouch, like stubbing your toe. Tonic pain is the longer-lasting, dull ache or throb that often follows. They use different neural pathways.
But pain isn't just about the stimulus, is it? The book stresses non-stimulus determinants.
Hugely important. Culture, expectation, mental state, they can dramatically alter pain perception. Think of athletes playing through injuries, or those Indian hook-swinging ceremonies where people report ecstasy, not agony.
It's mind over matter, to some extent.
To a significant extent. This led Melzack and Wall to develop the gate control theory.
Okay, the gate theory, how does that work?
It suggests that pain signals traveling up the spinal cord have to pass through a neural gate. This gate can be opened or closed by various factors. Pain signals try to open it, but other inputs like touch or pressure can help close it.
Like rubbing a sore spot makes it feel better.
Exactly. The rubbing activates other fibers that send signals to inhibit the pain transmission, close the gate. Crucially, the brain itself can also send signals down to close the gate.
Where does that happen?
A key area is the periaqueductal gray, TAGE, in the midbrain. Stimulating the PEG can produce profound pain relief.
And this explains painkillers and endorphins.
Yes, morphine and other opioids increase activity in descending pathways that close the gate. Our body's natural endorphins work on similar systems. It also helps explain stimulation-produced analgesia, like acupuncture stimulating certain nerve fibers, might trigger gate-closing mechanisms.
So pain is this incredibly complex interaction between sensory input and top-down control from the brain.
It really is a fantastic example of psychology and biology intertwining.
Which leads us squarely into that really difficult debate the book presents. Using opioids for chronic pain. Given everything we know about pain's complexity and modulation, how should we approach this?
It's a tough one, and the sources present two strong opposing viewpoints. On the one hand, Robert Jameson argues for opioid use in many cases.
These points.
Chronic pain is a massive problem, affecting millions, huge costs. Opioids are simply the most potent pain relievers we have. He argues fears of addiction are often unfounded for stable chronic pain patients, with low abuse rates and tolerance not always developing. The improved quality of life, he says, outweighs the risks for many. He cites studies showing benefits and stresses careful patient selection and monitoring. His bottom line is that undertreating pain is a tragedy.
Okay, a strong case for relief. What's the argument against from Dennis Turk?
Turk acknowledges opioids work for acute pain, but questions long-term use. He brings up Fordyce's idea that opioid use itself might reinforce pain behaviors. He also notes physicians sometimes prescribe for emotional distress, not just physical pain. Crucially, he argues concerns about addiction, tolerance, and side effects are not unfounded.
And he mentions hyperalgesia.
Yes, the paradox where long-term opioid use can actually increase pain sensitivity, making things worse. He also questions the evidence for long-term functional improvement, pointing out studies often show only modest pain reduction, are short-term, have high dropout rates, and some people improve after stopping opioids.
Plus the societal issues, misuse, diversion, deaths.
Exactly. Turk highlights significant problems with misuse and abuse. While some patients do benefit long-term without issues, he feels it's premature to recommend widespread long-term use, given the risks and often limited benefits.
So, two very different perspectives based on interpreting the evidence and weighing the risks versus benefits. No easy answers there.
Definitely not. It reflects the complexity of chronic pain itself.
Wow. What an incredible deep dive. We've really journeyed through the foundations of experience, haven't we? Unpacking how our senses take this overwhelming informational tapestry and somehow filter it, convert it, code it.
Into the neural signals that ultimately become our reality. From the physics-defying sensitivity of the eye to the intricate mechanics of the ear, the chemical senses, the skin, the profound complexity of pain.
And seeing that constant interplay, psychological experience, what things feel like, look like, sound like, tied so deeply to the underlying biology, the specific nerve energies, the opponent processes, the gate control.
It truly highlights how understanding the brain and understanding the mind go hand in hand. It's a testament to how elegantly designed, through evolution, these systems are.
Absolutely. So to leave our listeners with something to chew on, a provocative thought, perhaps.
Well, considering how remarkably we turn light, sound, chemicals, pressure into these rich experiences, what's next? Could we, through technology or maybe even future biological tweaks, develop entirely new senses?
Like sensing magnetic fields, or maybe directly perceiving things like X-rays or radio waves that we currently filter out.
Exactly. What information is currently invisible to us? And if we could perceive it, how fundamentally might that change our entire experience of reality?
That's a mind-bending thought to end on. Gives you a whole new appreciation for the senses we do have.